All right. Okay. So I'm going to pick up from where we left off in the last lecture. So I was trying to show you how to, different ways to write a function that dynamically allocates an array and then returns a pointer to the first element of the array back to the caller. Now the problem is when you dynamically allocate an array, C has no way to determine the size of that array after it's been allocated. Right? So all you get back from malloc or calloc or realloc is a pointer. Right? If you ask for the size of the pointer, you get back 8 or 4 or something. I can't remember what you get. You get back some number that's equal to the amount of space needed to store a pointer. Right? You don't get back the size of the array. And so that means if you just return a pointer to your allocated array, the caller has no idea how big that array is, which is a problem. Right? It might have 1 element in it. It might have 1,000 elements. They have no idea. Right? So the first first function that we had makes an array of a specified size. Right? Now in this case, it's fine. So the caller knows how big the array is that they want. So it's now the caller's problem to remember that they've allocated an array of size n. Right? But that's fine. Right? So this function works exactly the way you expect it to. Right? It makes a dynamically allocated array using malloc, fills in the values of the array, and then returns a pointer to the first element of the array. Right? And now the caller has to remember that the caller is responsible for remembering the size of their array. Right? The second version of a function that actually worked, right, was this makeArray2. So in makeArray2, it also returns a pointer to the first element of the array, right? But it stores the size of the allocated array in the variable num_elems, right? So in other words, because you can't return more than one value from a C function, right? You now need some way to convey the size of the array back to the caller. So we asked the caller to pass in a pointer to, in this case, a size type variable, right? A pointer to an unsigned int value, right? We're then going to internally in the function, we're going to dereference that pointer to get the variable or to get the object, the unsigned int object to store the number of elements in, and then we're going to set that value, right? So we're going to dereference the pointer. Right? And that lets me store the number of elements, or the size of the array, in whatever variable the caller has passed a pointer to. Right? And so this works fine too. Right? So this this returns the array, sets the value of the, and then sets the value of the size of the array in whatever that point's at. Right? Now you can flip these two things around, right? So I can return the number of elements that are allocated and then store the array in a variable that or store a pointer to the first element of the array in a variable that the caller gives me. And so that was the function that I was trying to write last time that never worked. So I'm calling it makeArray4 today, right? I've rewritten it slightly to clean it up. So this one returns the number of elements, right? And it takes in a pointer to a pointer in this case, right? So a pointer to an int, right? So what we're going to do is we're going to try to store the pointer to the first element of the array in whatever a points at. Okay. So a picture of this is so this is what I wrote last time, right? So we've got star a, so I'm going to dereference a. Right? Now, a is a pointer to a pointer. So when you dereference a, right, you get a pointer to an int. Right? So it's a pointer to an int. You dereference it once, you get a pointer to an int. Right? So that's actually a pointer to an int. Right? And I can store the result of malloc in that pointer. Right? So I need a pointer to something to store the result of malloc in, so I'm going to store it in star a. Then I'm going to try to fill in the values of a. Of star a, right? Now remember star a, that's a pointer to an int, right? So in other words, it looks like it's an element of an array, right? Square brackets I means the ith element of that array. right? I want to set that to I. Right? So that looks like it's okay, but if you actually run this program, this is when you get the segmentation fault that we were getting yesterday. So I've rewritten the program slightly. So when I call make array 4, that's when you get the segmentation fault. Now the question is why are you getting the segmentation fault? And the answer is as follows. So if you look up the operator precedence for the C operators, right? Anything that has precedence 1 has the highest precedence, right? So you see there's a bunch of operators that all have the highest precedence. Array indexing is one of those operators, right? So array indexing has the highest precedence, right? Which is a problem because your dereference operator has lower precedence, right? So it's got lower precedence. So when I write star A, right? Now remember star A, I want to get a pointer to an int, right? That happens after the array indexing, right? So this is why it barfs. This is why you get the segmentation fault. I'm going to try to index into what ends up happening is this is equivalent to writing the following, like that, right? So that's equivalent to taking my pointer to a pointer, right? And getting the ith element of that, right? And then dereferencing the value, which isn't going to work. So I'm going to draw a picture in a second to show you exactly what's happening. So to make that work, you have to tell C that you really want to dereference A first, and then access the ith element of that array. Right? So if you do that, the problem goes, that fixes the problem. Right? So recompile and run again, and there you go. Make array 4 now works just fine. So to understand what's going on here, it's useful to draw a picture. Right? So let's go back to here. That's why I also renamed the variable A here. So here I've got this thing called ARR. Right? So I've got a variable called ARR. Right? Its type is int star. Right? So pointer to an int. Right? We set it to null. So array points to null. Right? Now I'm going to call down here, make array 4, and I'm going to pass in the address of ARR. Right? So we're going to jump up to that function here. Right? So A is this pointer to a pointer, right, inside this inside the function. A has type int star star. Right? So pointer to a pointer. So what does that mean? A points at that thing there. Right? Because I pass in the address of ARR to the function. Right? So A points at that variable there. Right? That's what it's pointing at that variable. Right? It's not pointing at whatever that points to. A is pointing to that variable ARR. Right? So what is star A? So star A, so A points to there. That means star A is that object there. Right? Is that up? So star A equals malloc. So what happens? ARR now points to that array there. Right? So this array has size 100. Right? So that's what happens now. Now, inside the loop, right, when I write that, right, this is what I had yesterday. Right? So when I write star A square bracket I, right? So the A square bracket I happens first. Right? There's A, right? A square bracket 0, right, means that thing there, right? So when I write A star bracket 0, that's the first element of A, right? Well, A points to that thing there, so the first element of A is that thing there, is ARR. So what does that do? That sets ARR to 0, right? So in other words, that goes away now, right? And ARR points to 0, equals the value 0, which is null. Right? Right? If you set a pointer to null, if you set a pointer to the value 0, it gets set to null. right? Which is actually fine, so that actually works. The problem is on the next, oh, and then you dereference it, right? Sorry, I'm sorry, wait, what am I, hold on, sorry, back that up a second. Sorry, back that up. Hold on, that's wrong, okay. Okay, so a square bracket 0 points to that thing there, right? I then dereference that thing there and set its value to 0, right? So now I dereference that, right, and try to set it to 0, right? And that's the problem. That's what, and that's actually the problem, right? Because this thing here, ARR, is actually a pointer, right? So when I dereference it, what do I get? What is it pointing to begin with? Wait, sorry, hang on. So I did the malloc, right? Oh, okay, never mind. I did the malloc, so that's fine. So it's going to set that value to 0. What happens the second time? Right, so what is A1? Right? Well, if that's A0, right, A1 is whatever sits in memory after ARR. Right? So it's actually whatever's sitting here, which is nothing, or I don't know what's there. Right? It could be anything that's sitting there, right? And so eventually when you run this loop long enough, right, so now we now try to set what we dereference whatever's sitting here and try to set its value, right? So that's when it barfs, right? What you really want to do is you want to go into here, right, and then set that value there, right? So to do that, right, I have to dereference A first. Right? So dereference A means get this object here, right? Now ARR0 is that, right? Then ARR1 is that, and then ARR2 is that, right? So it was all a precedence problem that was caused there. Now, you can rewrite this so that it's a little clearer. So let's make array 3, right? So this is exactly the same code. So what I'm going to do here is I'm going to make my array separately. So I'm going to call it, I'm going to make a pointer B, right? And that's going to point to the first element of my newly allocated array, right? Then I'm going to fill in my newly allocated array, right? So this is just make array 2 all over again, right? 2 or 1, one of the two, right? So that's fine. So I filled in all the elements of the array, and now I can write star A equals B, right? So in this picture, you get the following. Right, so we're going to call the method like that. Right, so so A is still going to point at the array variable. Right, but now we've got this thing called B. Right, and its type is int star. Right, we call malloc, so B points at that array. Right, you now fill in the values. Right, so 1, 2, 99, right? And now I write star A equals B. So what's star A? Star A is that thing there, right? So that thing there now points to that array there, right? And so that's probably, well, that might be a little easier to understand, right? But the array 3, make array 3 and make array 4, they're completely equivalent. Right? They're just, it's just I've introduced a separate variable here, right? Rather than always dereferencing A, right? All right, clear as mud? Yes. Okay. All right. Any questions? Okay. Oh, so yeah, if you actually run the program now, you can use all three, right? So you can use the original version, not the original version, the second version. So the second version, we store the number of elements. The caller passes in the address of a variable in which to store the number of elements in, right? So that works fine, right? We still get 100 elements. We still generate the array, right? Version 3 and 4 are functionally equivalent, right? Here, we return the number of elements, and the user passes in the address of a pointer, which points to the first element of the newly allocated array. Not that one, this one. All right. Okay, so that's it for arrays for the time being. Sorry about that. So I now want to talk about this thing called typedef and C structures. So there's this, there's a statement called typedef that lets you declare a name, so an identifier, right, as a type alias to be used to replace a possibly complex type name. So in other words, what that means is if you've got some complicated type name, and type names can get very complicated in C because of pointers, right? You can replace that with an easier to read name using a typedef statement. Right? Now, this doesn't actually create a new type, right? It simply says that the alias can be used in place of the actual type, right? So the syntax looks like typedef some type, and then the new name for the type, or the alternative name for the type. Right? So type is some existing type, alias is just some new name for the type. So for example, this thing CISC220, that's actually a typedef. Right? So it's a typedef for a long unsigned int. I always thought it was unsigned int, but I guess it's long unsigned int. Right? So rather than writing long unsigned int everywhere, you can just write CISC220, right? Which is a little bit more convenient. This thing called pointer difference underscore t, right? That's what happens when you subtract, that's the type that's used to represent the difference between two pointers, right? So if you write a minus b, where a and b are two pointers, then the type of the returned value is long int, right? And so instead of writing long int everywhere, you can just write pointer diff underscore t instead, right? Now, CISC220 is not a new type, right? It just means, it's just the short form for long unsigned int. Right? Pointer diff t is not a new type. It's just short form for long int. Right? It's a little easier to understand. It's a little easier to write. And it probably, when you're reading your code, it makes, it's a little easier to understand what the variable is being used for. All right, so typedef is usually used to simplify writing complicated types and to provide what are called incomplete types. Right? So, okay, so the first one's actually a little hard to read. So int star, there's your type, right? Now int star, that's a pointer to an int, right? I can give that the name int pointer underscore t, right? So whenever I write int pointer underscore t, right, that's indicating to you that the variable type is a pointer to an int, right? F pointer t is a pointer to a function that returns an int and has two int parameters. So this is a pointer to a function. So we're going to look at these in more detail later. Right? For now, this is just an example. So typedef, right? The typedef for function pointers is weird. So the name of the type is, the name of the alias is here. Right? So fptr underscore t is the name of the alias. Its actual type is a pointer to a function that returns an int and takes in two int parameters. Right? So we'll revisit pointers to functions a little bit later in the course. Right? This one we're going to look at tomorrow, I think. Tuesday. So struct list is our type, right? And list is the name, is the short form for the name. Right? So list is an alias for this thing called struct list. Now I actually haven't defined what struct list is anywhere yet, right? But in C, this is a perfectly reasonable line of code to write. Right? So struct list is an undefined type, right? And list is an alias for that type. Right? So as far as the C compiler is concerned, that's perfectly fine to write, right? Even though it doesn't know what struct list is. Sorry. Okay, so here's an example of using a typedef, right? So this is exactly the same. This is very similar to the code that I just showed you, right? I'm going to make an array, right, of n elements, right? Notice there's size t, right? So you're already using a typedef here, right? Instead of returning int star, I can write return int underscore pointer underscore t, right? Because int underscore pointer t is just a type def for an int star, right? Is this easier to understand? Probably not, right? This is not a great example, but it's a simple example of using a type def, right? So rather than writing int star everywhere, you can just write int underscore pointer underscore t. Same here, right? So when you declare when you get the return value from make array, instead of writing int star, you can write int underscore pointer underscore t. Right? So all a type def does is it lets you create a new name for an existing type, or for a potentially existing type. Right? Now, what are structures? So a structure in C, or a struct, right, is sort of like, is kind of like a Java class that has no methods, right? So in other words, it's sort of like a Java class that just has some fields, right? That's sort of what it's like. So a structure or struct consists of one or more members, those are just variables, right, whose storage is allocated in some ordered sequence, right? For our purposes, this ordered sequence business is not that important. Right? When you get into slightly more advanced C, the fact that C lays out structs in a particular way becomes more important. Right? For us, it's not that important. Right? All that's trying to say is that a struct is just a group of variables, right, in one block of memory having a single name. Right? But that's sort of like an object. Right? So an object that has fields, right, is just some chunk of memory that's got some variables in it. Right? So it's sort of like a Java class having no methods. What's the syntax? Well, it's struct. There's something called its tag name. Right? That's just the name of the structure. Right? And then you just list a bunch of variables. Right? So some type followed by some variable name, some type followed by some variable name, and so on and so on and so forth. Bye. Right, so if you took CISC220 with me, right, you looked at saw the point2 class in Java, right? If I wanted to make a point2 quote unquote object in C, I can use a struct, right? So struct point2, right? So every point has an x and a y coordinate whose type is double, right? So that's it has no methods, right? So in C, there's no way to tie specific functions to this structure, right? So inside the structure, I can't declare any functions, right? But I can declare all the variables that belong to a point2 object, right? Now the type name of this is struct point2, right? So if you want to use this thing, right, I can make a variable of named p, whose type is struct point2, right? And then I can use the members x and y using the same notation that you use in Java, right? P.x is the variable x belonging to this structure p. Right? P.y is the variable y belonging to that structure variable p. Right? So every time you make a new struct point2 variable, right, it has two members x and y. Right? So if I wrote struct point2q, I could write qx and qy. So in other words, there's no constructor, right? You don't have to write a constructor for this. You get a chunk of memory, right? That has a field called that has a member called x and a member called y. Right? This actually works. You'll get 0 and 0 in this case if you run this program. I don't know if I have this program here. I don't think I do. Why did that happen? LSST. What? Anyway, I don't have that program here. If you run that program, though, it'll print out 0 and 0. Okay, now if you, writing struct something all over the place is sometimes inconvenient, right? So if you want to, you can create a type def for struct point2, right? So that's the type, right? Struct point2 is your type. I can make a type def for that type, and I'm allowed to use the same name as the tag name, right? So in other words, I can reuse that name as the type def name. So I can write type def struct point 2.2, and that just says that wherever I would used to have to write struct point 2, I can just write point 2. This doesn't have to be the same, right? If you want to give it some different name, that's fine, right? If you want to call it PT, that's fine, whatever you want, right? You can give the alias name can be whatever you want, right? And now I can just write point 2p, right? And then use px and py, right? So that simplifies things a little bit, I guess, kind of, sort of, right? If you do an internet search about whether or not you should type def a struct or not, you'll get all sorts of various opinions, right? In particular, what's his name? The Linux guy, Linus. He does not like using a type def for structures. He thinks you should just write struct blah everywhere. Whatever, right? It's up to you. Initializing members. So the members of a structure can be, you can initialize them using a syntax that's the same as array initialization. Right? So in other words, I can write point 2p equals braces, and then I can fill in the values of x and y. Right? So let's look at an example here. Right? So I can write p equals brace 2, 3. Right? And that sets x to 2 and it sets y to 3. Right? So if I print out px and py, I get 2 and 3. Right? So this is an initialization though, right? So when you can only do it where you declare the structure variable. Right? So I can't write point 2p semicolon and then on the next line write p equals brace 2, 3. Right? That's not initialization, that's assignment. Right? You can also specify the name of the members explicitly. Right? So point 2q equals brace, dot x means set the x member of q to 1, comma, dot y equals 1.5 means set the y member of q to 1.5. Right? And then finally, you don't have to set all the members if you don't want to. Right? So I can write r equals dot y equals minus 3.1, and that sets the y coordinate to minus 3.1. Members not explicitly initialized are 0 initialized. Right? So in the bottom example, I did not initialize the member x to anything, so it gets initialized to 0 automatically. Right? So that becomes 0, that becomes minus 3.1, and you get r colon 0.0 comma minus 3.1. Right? Okay, so structs are like a poor man's class, right? That's basically what that's one way to think about it. A long time ago, they were called things. They were also called records, but that's going way back to the Pascal days. Okay, so if you have a struct object, you can access the members using the dot operator, right? So I've got, right? So here, P, Q, and R, right? They're all struct point 2 objects, right? Now, if you have a pointer to a structure object, right? You don't use the dot to access the members, right? So when you have a pointer to a structure, you use the hyphen greater than. So that's the arrow operator, right? So this thing here automatically dereferences the pointer and then gives you the member, right? And then accesses the member, right? So here's pointer, right? So PTR, that's a pointer to a point 2 object, right? So it's a pointer to a structure, right? I can take the address of P and store that in the pointer, right? So in other words, PTR points to that struct object right there, right? If I want to change the value of that object, the value of the members of that object using the pointer, right? I write PTR minus or hyphen greater than x, right? Equals 200, and then PTR arrow operator y equals 300, right? Alternatively, you can dereference the pointer yourself, right? So alternatively, this is the same. Oh, sorry. That's equivalent to, dereference the pointer, and then write dot x equals 200, sorry. right? And this is the same as star dereference the pointer dot y. Right? So instead of dereferencing the pointer explicitly yourself, right, you can use the I guess it's the arrow operator. I don't actually know what it's called. But anyway, you can use the hyphen greater than to do the dereference for you. Right? Either way you write it, it's fine. Right? It doesn't matter how you want to write it. Now, on structures, you can assign them to other structure variables, which doesn't work in Java, right? So if you write x equals y in Java, where x and y are both references, that doesn't actually copy y and assign it to x, right? In C, it actually does do the copy for you, right? So in other words, you get a member by member copy, right? If the struct contains a pointer, you have to be a little bit careful, right? So if one of your members of the structure contains a pointer, sorry, if one of the members of your structure is a pointer, right, then when you do the assignment, you end up with two structure objects containing a pointer that both point to the same thing, right? So here's P, right? It's the point 2, 3. There's Q, right? It's the point 0, 0 at this point in time. Right? If I write Q equals P, right, that copies the value of 2 into Q dot X, and it copies the value of 3 into Q dot Y. Right? So when you print out Q, you get 2 and 3. Right? It doesn't change P. Right? So it doesn't change P. If you write QX equals 200 and QY equals 300, right, P doesn't change. Right? So P and Q are two separate structure objects, right, having their own separate members X and Y. Which is very different than what happens in Java, right? Because Java uses references for everything. Can you dynamically allocate a structure? The answer is yes, you can dynamically allocate a structure. You can actually get the size of the structure too. So if you ask for the size of the structure size, right? So malloc, you have to specify how much memory do you need, right? You can get the amount of memory needed to store the structure object by just using size of, right? So size of 0.2 returns the amount of memory needed to store 0.2 object, right? In this case, the language guarantees, I'm pretty sure it guarantees in this case, that the size of this structure object is equal to 2 times the size of double. So I can make a pointer to a 0.2 object, right? And then I can set the members X and Y of the structure object by dereferencing the pointer, right? And then accessing the member, right? So again, you can write P arrow X equals 100, or you can write star P in brackets dot X, right? Either way is fine. Okay, comparing structures for equality, right? So in Java, if you want to compare if two objects are equal, right, you override equals, and then you just use the equals method to compare two objects for equality, right? C doesn't have any built-in mechanism for comparing two structures for equality, right? So in other words, if you write equals equals or not equals to compare two struct objects, it's undefined, right? The compiler will flag it as an error. Right? Now, so you have to ask yourself, what does it mean for two structs to be equal? Right? And this means you have to decide what equality, so you have to decide what equality means, and then you have to compare the relevant members yourself. Right? If you need to do this more than once, you should write a function, obviously, right? So if I want to compare if two, oh, here we are. Right, so here's, this is comparing whether or not 2 points are equal, right? Where I have Q, Q is a point, P is a pointer to a point, right? So P is a pointer to a point to object. So if I want to compare if the object pointed to by P has the same coordinates as Q, I've got to do a lot of work myself. Right? I have to look at the x coordinate of the object pointed to by P. Right? So dereference P, get its x coordinate. Check if that's exactly equal to the x coordinate of Q. Right? And then check, is the y coordinate of the structure pointed to by P equal to the y coordinate of the object Q? Right? If you have to do this more than once, write a function that takes in this case, a pointer to a structure, and then a structure object, and then does the comparison inside the function, returning true or false. Right? You should probably write in this case, you should actually probably write a function that takes in 2.2 structures, and then compares the coordinates of the structures. Right? Okay, so that's structures and type defs in 30 minutes, I guess. What time do we have here? 10 after. All right. Okay, so the next thing we're about to do in this course is that we're going to implement a data structure in the course. So we're going to implement a list. Right? So remember array list from Java? If you took 124 with me last term, you actually implemented one of these. I don't remember if we did it last year or not. Anyway, we're going to implement an array-based list in C. Right? Because C doesn't have any lists. All it has are arrays. Right? If you want like a list or a set or a map, you have to find a library that implements it for you, or you have to roll your own. Right? So we're going to write our own implementation of an array-based list. But to do that, we need to know how you actually organize a C program. Right? Because what I want to do is I want to create an array-based list, and I want it to be reusable. So I want anybody to be able to use this list. Right? But in order to do that, I have to tell you how you organize a C program. Okay, so in a C program, you've got these things called header files, right? So we've seen these sort of already, right? We've got math.h, we've got standardlib.h, we've got standardio.h, right? So what does a header file actually do? So a header file simply declares a bunch of types, and it simply declares a bunch of functions that might operate on those types. Right? So when you create a new type, such as point2, right, it's often the case that you want to create functions to accompany the type. Right? Now, what do you do in an object-oriented programming language? You make a class. Right? You put the fields, the coordinates of the point inside the class. You put all the methods that operate on a point inside the class. Right? So in Java, you would bundle up the fields and methods into a class. Now, there are no classes in C, so what do? Right? So in C, you take your type declaration and all your function declarations, and you put them into what's called a header file. Right? So now these are the declarations, right? They're not the definitions. So I declare my types, I declare my functions, but I don't define the functions. Right? And I put all of those things into a header file. Right? So in C, a header file always has the extension .h. Right? So in a C program has .c files and it's got .h files. Any C source code file that includes your header file can now use your type. Right? So if I make a list.h that defines the list type, an array-based list type, right, and all the functions that work on that list, right, then all someone has to do is include list.h into their program, and they can now use your list type. Right? So this is sort of like importing a class in Java, but it's not exactly the same mechanism. Right? So if you only declare the functions in the header file, where do the definitions go? They go into a separate C source code file, possibly more than one, right? But normally it goes into a single, often it goes into a separate single C source code file. Right? So what point2 functions might be useful for someone using the point2 structure? Right? So it might be nice if I can move a point. Right? So if I have a pointer to a point, right? Okay, so I have a pointer to a point, and I want to change its coordinates by delta x and delta y, right? I can provide a function that looks like that. Right? Suppose I want to take a point and I want to multiply its coordinates by some scalar value s. Right? Well, I can write a function that takes in a pointer to a point and a double value s to multiply the coordinates by. Right? Equals. I want a pair of 2 points are equal. Right? I can take in, oh, this is interesting. All right. I can take in 2 point objects, P and Q. Right? Notice that I marked them const in this case. Right? Why did I mark them const? Because equals should not change the coordinates of a point. Right? So if I mark P and Q as being const, I will not be able to inadvertently change the coordinates of P and Q inside that function. Right? ToString, right? So I want to be able to print I don't want to be able to print. I want to be able to generate the string representation of a point, right? So I can take in a point object, right? Mark it const to indicate that the function does not actually change the point, right? And return a char star, so an array of character that is the string representation of the point. Right? And you can go on and on and on and on, right? There's lots and lots and lots of functions that you could define for points. Right? Let's see, do I actually have it? Oh yeah, I'm going to do it here. Okay. What time is it? Sorry. Okay. All right, so when you make your header file, the very first thing that you should put into the header file is something called an include yard. Right? So I'm going to define my point2 type inside the header file. I'm going to declare all of the functions that work with point2s inside the header file. Right? When I make the header file, the first thing you do is you write what's called an include yard. The include yard prevents the header file from being included in more than once in a compilation unit. Right? So remember what include does, right? So if someone writes include point2.h, right? The preprocessor takes the contents of point2.h and drops it into the C source code file. Right? So it literally copies the contents into the source code file. Right? If someone includes another header that also includes the point2 header, right, what ends up happening is a second version of the point2 header gets dropped into your program. Right? And that's an error. Because now you're defining the point2 type twice, and all of the functions you're declaring twice, right? Which you can't do inside of a single C source code file. So you have to prevent your header file from being included in the same source code file more than once. And that's the purpose of the include yard. Right? So the way you define the include yard is as follows. Right? So this is your header file. Right? So this is going to be point2.h. And what you do is you write if ndef, so hashtag if ndef point2h. Right? So point2 underscore h in all caps, that's just a name. Right? So that's going to be the name. That's going to be the name that I associate with my header file. Right? If ndef means if this name is not defined yet. Right? So if this name is not defined yet, right? Do everything that's in between the if ndef and the end if. Right? So this end if ends this if ndef statement. It's not technically a statement. It's a directive. It's a preprocessor directive. All right. So if I haven't defined point2h yet, then everything inside, everything in between, I guess runs or gets included in the. Well, okay, we'll just say it runs for now. Right. So if the point2 if that name hasn't been defined yet, I'm going to define that name. Right. So define is the preprocessor directive that says the name point2h now exists. Right? And now every time the preprocessor tries to include this header file, right, it sees that point2h is defined, so if ndef is false, and it just ends up down here. Right? So in other words, the preprocessor will not include this header file in a file twice. Right? So that's the structure of an include yard. All right? Okay, so what does the rest of the header file look like? I'm going to include standard bool because I want equals to return bool. Right? There's my structure for point2. Right? There's my type def for point2. right? And here are all the declarations for my functions in the header file, right? So whenever somebody includes this header file, they get the definition of the structure, they get the type def, so that they can use the name point2 instead of struct point2, right? And then in the C source code file that they're writing, they can use any one of these 4 functions, right? What's next? Okay, so where do you actually define these functions, right? Well, you define them in the C source code file point2.c, right? So this is point2.h, right? All of the functions now go into point2.c, right? And the first thing you do in point2.c, or not necessarily the first thing you do, but what you have to do is you have to include your header file, right? So you include point2.h. Now, this is a header file that we made, right? So it's not one of the standard library header files. So if it's a header file that you made, to include the header file, you have to use the double quotes, right? The less than and greater than sign, those are meant for the standard library header files. Right? Any user-created header file, you include with double quotes. Right? And now you just define your functions. Right? So now you take your functions and you give them an actual definition. So how do I move a point pointed to by p? Right? Well, I just add dx to the x coordinate. I add dy to the y coordinate. Right? How do I multiply a point pointed to by p by s? I just multiply the x coordinate of p by s, and I multiply the y coordinate of p by s. Right? How do I check if 2 points are equal? Right? Now these aren't pointers, right? These are actual point2 objects, right? So I just check if px equals qx and py equals qy, right? Notice this does not handle nan correctly. Right? So if your point2 object needs to handle not a number as a coordinate correctly, you have to do something else here. Right? If you've got not a numbers happening in your program, though, you've got other problems. So for the time being, this is fine. What about toString? So toString is surprisingly complicated. So remember in Java how you implement toString? You would just write like square bracket plus px plus comma space plus py plus square bracket, right? Nice and easy. It's not that easy in C, right? It's a bit of a disaster in C. Okay, so how do I get the string representation of a point? So remember, I have to return, strings in C are just character arrays, right? So I have to dynamically allocate a character array and then populate the elements of the array, right? Now, your very first problem that you run into is how big is the array that I'm allocating, right? So without any other explanation for the time being, right, I'm going to allocate an array of size 34 apparently. Okay? So I'm going to allocate an array of size 34. So there's my malloc for the character array, right? Now remember, malloc can fail, right? So if you run out of memory, malloc fails. So I have to check if the return pointer is actually not null, or in this case is null, right? So if the malloc fails for the string, I'm going to return null, right? Which means whoever's calling point2 to string, if they're paranoid, they need to make sure that the string, the character array that's returned is not null. Right? Now, how do I populate the array? Right? So in other words, how do I generate the string representation of the point? I'm going to use this function called sprintf, sprintf. So formatted print into a string. That's what it's short for, right? S is the string, printf is formatted print, right? So how does this work? You pass in the array where you want to put the formatted string, right? So that's buff. The next part is the formatting string itself, right? So this tells sprintf how to convert px and py into characters, right? So inside the formatting string, you can put whatever text you want. So I'm going to put in the round bracket, a comma, a space, and a round bracket, right? So my output string is going to start with a round bracket. In the middle, it's going to have a comma and a space, and at the end, it's going to have a closing round bracket. %G is one of the conversion formats one of the conversion specifiers that you can use for float numbers, for floating point numbers, right? So it's going to convert the floating point value of px using this %G conversion, and it's going to convert p dot y into using this %G conversion, right? I'm going to explain to you next class what these do exactly. Right? I just want to look at the function for now, right? But for now, all you need to know is that px will be printed into here, and py will be converted into a string here, right? Okay, now printf, all the printf functions return an int value, right? So they return an int value equal to the number of these things that successfully convert, right? So in other words, if I can successfully convert px using %G, and I can successfully convert py using %G, sprintf will return 2, right? So it returns the number of successful conversions, right? If that number is less than 0, some sort of error has happened, right? Int n, sorry. Back up a second. sprintf doesn't do that. sprintf returns the size of the, does it return the size? N is greater than or equal to the buffer size. Printf returns the, it returns the buffer size, really? N is greater. I guess it returns the number of characters, hang on, where's, oh, I don't have it here. It's going to return the I should look it up before I tell you what it is. It's going to return the number of, the length of the string that's converted, I think. So C, headers, and this is going to be, are we out of time? Oh yeah, we're out of time, sorry. I guess I'll pick this up next class and explain the %G and what sprintf returns better in the next class. Any questions before we go? No? Your next assignment comes out later this afternoon. It's just about done. It's just basic programming in C. So the first 2 questions are very short. The third one is a little longer, but it's not that long. Right? You should be able to easily do it before the due date.